Hello and welcome to our lecture on Chapter 16. We're going to start a segment in which we move out of talking about the geosphere and elements of the hydrosphere, such as the oceans, and we talk about the atmosphere. And we'll talk about the atmosphere for around 4 lectures, chapters 16, 17, 18, and 19. In this chapter, we're going to focus primarily on the atmosphere, and that's going to set the foundations for understanding a little bit more about things occurring in the atmosphere, like precipitation, the development of different kinds of weather fronts, severe weather, and so on. All those are tied up in kind of the fundamentals that we'll talk about now. And so for this chapter, we'll focus on atmospheric composition, just the elemental makeup, atmospheric structure, and then we'll move on to talk about the effects of pollution. There are a number of ways in which we can pollute the atmosphere and contaminate it. Even CO2 now is considered to be pollution. And then we'll talk about solar radiation and heat. So really we're going to focus where solar radiation and heat interact with at the Earth's surface or near the Earth's surface, and then finally wrap up with global temperature distribution and the causes for those global temperature distributions and some of the mitigating factors. So the Earth has 3 main components in its atmosphere. We have major gases, we have trace gases, and we have something else called variable components. The modern atmosphere consists primarily of carbon dioxide, of nitrogen at 78%, and 21% oxygen with minor amounts of argon and carbon dioxide. And it's a lot different from the early atmosphere, which was almost 80% carbon dioxide. So the Earth's atmosphere is not static. It is changing and has been vastly different in the past, but not the near past. Okay, those high degrees of carbon dioxide would have been way back in geologic time during the Archean and the Proterozoic, so in the Precambrian super eon. The atmospheric gases are interacting with rock and are stored in rock, so there's quite a bit of CO2, for instance, stored in dolostone and limestone. Those rock types occur in vast quantities over the Earth's surface. And then we have gases dissolved in the ocean and gases dissolved in the atmosphere, which interact with the ocean. And so there's a kind of equilibrium there where gas is moving from the ocean to the atmosphere, or potentially from the atmosphere into the ocean. Now, the more CO2 we put into the atmosphere, the more it builds up in the atmosphere, and that will actually push some CO2 into the oceans, and that raises the ocean's acidity, which is causing some problems in some areas where organisms that make their homes or their skeletons out of limestone. Limestone then becomes unstable in low acidity environments, and we call this process ocean acidification. Why does it matter? Well, it doesn't necessarily matter if you don't care about the skeleton of an algae, or the life of an algae, but it's typically going to affect organisms within the broader food chain. So that's a bigger problem. Not only are we going to be losing things like the Great Barrier Reef, right, which are complex ecological systems, but we're also attacking smaller organisms that make up a big part of the food chain. So most of the atmosphere, again, nitrogen with lesser amounts of oxygen. Trace gases, consist of this small percent, less than 0.1% or 0.1%. You can see them here, okay, trace gases, and we'll just jump over to the right and see what they're made up of. So our trace gases are relatively small. Most of those trace gases are made up of carbon dioxide, okay, followed by neon, so an inert gas, and then lesser amounts of nitrous oxide, methane, and helium. Okay? And even even in this tiny fraction of those gases, of the 100% of those gases, occurs as ozone or O3. Of the gases that are problematic for us with regard to greenhouse gases, we can check off just a few: methane, nitrous oxide, ozone, and CO2. So many of the trace gases that are in the atmosphere are also greenhouse gases as well. And there is a reasoning behind that. The variable components are called variable components because they don't exist in the same quantities across the globe. The major and trace components are what I'll say are well mixed throughout the atmosphere, and so we don't necessarily expect there to be much difference in, let's say, nitrogen or oxygen levels between Illinois and Texas, right? However, we do find that we've got variable components that are not well mixed or are anthropogenic, so they're generated by humans, so locally generated. One of those variable components, which I have not mixed or really mentioned here, but is fairly common as a greenhouse gas, is H2O, right? So it is sourced from oceans, from lakes, and different parts of the country. In the U.S., will have different humidities and different amounts of H2O within them based on the local water sources, based on your latitude, and so on. But other things that are locally generated, things that might be generated more in particular in cities, we can come up to the diagram on the left. We see the mechanisms that generate different kinds of variable components. Most of these are pollutants, okay? So, for instance, transportation, just driving your car, most of the transportation, shipping, trucking, aeroplanes, all those things are contained within there, or make up about 49 or 50% of the variable components that are in the atmosphere, with the exception of H2O, which is a naturally occurring one. Fuel burned in factories and power plants makes up another quarter or so, a little bit more. And then we have miscellaneous things like solid waste disposal, which tends to result in the production of methane as materials biodegrade or degrade within landfills. And then evaporation of volatiles. Volatiles come in a lot of different forms, but the simplest one you might be most familiar with would be something like paint thinner or acetone. Anything that someone uses, for instance, to thin out various kinds of paints. So if you ever painted anything, interior or exterior on your house, or maybe you do this as a job too, you know that there's gases coming off of those paints. And so those are the sources of volatiles. And the gases are there to keep the paints liquid, and as the gases evaporate into the atmosphere, the paint dries, right? The distribution of these in terms of the pie chart on the right. So we have mechanisms in which they're formed. Pie chart on the right is showing us the kinds of volatiles we have. We have nitrogen oxides. Those are called typically shortened to NOx, N-O, and then small x. Okay, sulfur oxides, which we call SOx, NOx and SOx. Carbon monoxide, a lot of that's coming from transportation. Particulates are interesting. So this would be like soot. Okay, and so if you were to take, for instance, any of these components, so you took 1% slice out of the transportation here, right? That 1% would contain some percentage to make up, particulates, NOx, carbon monoxide, sulfur dioxide, and then also things like H2O comes out of the back of your car. So this is 100%, and then if you were to look at transportation, some different proportion is going to come from volatiles nitrogen oxides, sulfur oxides, carbon monoxides, and it'll be within this sort of 1% of the transportation material. So the components are on the right, and the total distribution of how we make them on the left-hand side. And again, they're variable because, well, they're not well mixed throughout the atmosphere for a couple of different reasons. One of the consequences of having NOx and SOx, for instance, so here's our sulfur dioxide, okay, and our nitrogen in the atmosphere, the nitrogen oxides, is that they make strong acids within the atmosphere. And that has caused issues in the past with gases heading up into the atmosphere, mixing with water and creating a sulfuric acid, or even nitric acid, and then an acid coming down into or in the form of precipitation. And on the bottom left here, you'll see that we've got a map showing the pH on the bottom. So remember, pH of 1 is very acidic, pH of 7 is neutral, and pH of 14 is very basic. And so on the west coast or the western half of the U.S., those pHs are around 5.5, so water's a little on the acidic side. But in certain industrial areas, especially along the east coast and up into the Great Lakes area and areas around Canada, we start to see pHs drop to into the 4s. And so the consequences of this, are variable. One of them is that you acidify ocean waters, but stream and lake waters as well, and that causes ecological problems, but also will corrode metals. And you can see here in the image on the right, you've got the face that's been etched off of what is essentially limestone, right? And you remember back to where we talked about limestone reacts with HCl. It'll actually react with a lot of different acids, and so it's basically just breaking down the rock. One of the other things that's out there in the atmosphere as a variable component is O3. Now, O3, which is known as ozone, is typically formed in the stratosphere, which is one layer above the layer we're in right now. We're in the troposphere. And it tends to be toxic to human beings, but it's also very necessary. And I'll talk about its function later on. But one of the problems is when the O3 comes down into the troposphere. This is a bad thing for us, or we have a buildup of O3 in the troposphere, and that can happen in a number of ways, and it is connected to anthropogenic pollutants that we put into the atmosphere, primarily through industrial mechanisms. So generation of electricity and transportation. 3/4 of the pollutants that go into the atmosphere are generated from those two areas. The idea here is basically that if you take something like a CFC, what's called a chlorofluorocarbon, CFC, and you bombard it with ultraviolet light, UV light, it's going to cause a chemical reaction. And this is not unusual to have light cause a chemical reaction. It ends up kicking off a chlorine atom, okay? And now that chlorine atom is out in the atmosphere, and it's pretty reactive. And so what it ends up doing is it will strip off oxygens from the O3, and it will end up making O2 out of that, and then it can actually, circle around in the system. So we can destroy ozone by adding CFCs. And if we back up for a second, we've got the density or the thickness of the ozone layer, which we need to protect us from ultraviolet light, is getting thin or has been getting thin around the polar regions. Now, it's normally going to be thinner around the polar regions simply because there's less ultraviolet radiation there in the first place. But adding CFCs to the system, chlorofluorocarbons, was actually making that hole or that thin zone even bigger. And the issue is that the Cl resides in the Earth's atmosphere for a long time, so it can come down and then it can dump off its oxygen and sort of lose it in the lower atmosphere, making O2. That's fine, but then it goes back up into, let's say, the stratosphere, picks up or interacts with another O3, picks up another oxygen, and so it just cycles around. In other words, it has a long residence time in the atmosphere, and so it's difficult to get rid of. Okay? And then its effectiveness is a function of solar radiation, so what latitude you're at in particular, and then to some degree with temperature of the atmosphere as well, so winter versus summertime conditions. If we add in NOx and SOx, so these are nitrogen oxides and so on, they also have the effect of interacting and making O3 in the lower atmosphere in some cases. And so where we want O3 up here in the stratosphere, well, we put in chlorofluorocarbons and it starts to break it down. And then we put SOx and NOx in the lower atmosphere and they make O3. And as I said, O3 is toxic, so it causes eye irritation and respiratory problems and so on and so forth. So by polluting the system, we're actually redistributing ozone into places we don't want it and taking it away from places that we do want it. The ozone depletion is possibly getting a little bit better. Like I said, we've stopped producing as many chlorofluorocarbons, so we stopped using aerosol cans in the same way, constructing them using the same chemicals. And this is back in the mid-'80s where this was detected, and by the mid-'90s, it was sort of became an international effort to stop the production of CFCs. But we still see, that there's a pretty big hole, especially in the Antarctic ozone layer, and that is possibly getting a little bit smaller. So maybe we'll find out some more on that as we move through the atmospheric discussions here. But more or less, it's been about the same size since we detected its depletion in the 80s. All right, I'm going to go ahead and stop talking about contaminants. Just to sum up, we talked about the composition of the atmosphere, and we talked about major trace gases, which are well mixed throughout the atmosphere, and then these other things that are variable components that are either anthropogenic, sort of produced by human beings, a function of geography. So you're going to get more smog and ozone production in cities than you are in, so in Chicago, for instance, than you are going to get in DeKalb. But we also, then we have to factor in other things that we put into the atmosphere that are still hanging out there, like chlorofluorocarbons, and are difficult for us to extract from the atmosphere. We'll move on to talk a little bit about the atmospheric structure and defining the different layers in the atmosphere, as well as pressure in the next segment.